Hi guys, in this video I'm going to present SN1 mechanism in halogen derivatives. Alright, so we start with this molecule. Now if you check this out, this is methane, ethane, propane, butane, tertiary T-butyl chloride. I am reacting it with sodium hydroxide. Now sodium hydroxide I have just represented it in terms of OH minus, which is a nucleophile. What do you mean by nucleophile? Nucleophile is one which has excess of electron or is negatively charged. Nucleophile, nucleus loving, nucleus is positive, so it has to be rich in electrons. All right, so that is what it is. All right, okay. Now if I see the structure over here, it would be tetrahedral structure and sp3 hybridized state. All right, okay, all and Cl assume it to be in the top. Fine. Okay, so what happens in step 1? In step 1, sodium hydroxide is there. Now Cl is electron withdrawing group, so it picks up electron towards itself and this bond is broken. As a result of this forms Cl minus and this forms carb cation. Alright, so carb cation is formed. What happens? What structural change does occur? Now from tetrahedral structure it has gone to trigonal planar structure. Trigonal planar. Now if you check this out, this is what is. If you check this out, this is what is tetrahedral structure. Now assume that this is Cl and this is CH3. So this is what is tetrahedral structure. Now here the Cl has disappeared, so it has become a planar structure. Now you see a bit of bending. That bending won't be there. Alright, it would be just straight like this, flat. Alright, so trigonal. So this is, so what all changes have occurred? From tetrahedral structure, it went into trigonal structure, trigonal planar structure, from sp3 hybridized. So this was three-dimensional structure and this is two-dimensional structure. This was sp3 hybridized state. This is sp2 hybridized state. There was no charge, whereas here it is carb cation now, positively charged. Alright, and the bond has broken over there in this step 1. Now let's see what happens in step 2. Now since it is C plus over here, carb cation, and we have got OH minus over here, so this does a nucleophilic attack on this carb cation. Alright, fast nucleophilic because it is in between charge. Alright, so when it does so, now how does it do this? Now in this case what happens is, since it's a planar structure, so OH can attack from top or OH can attack from bottom. So 50-50% chances are there for OH to attack from top as well as from bottom. Alright, so let's understand. So here OH is attacking. Now planar structure, OH minus is nucleophilic attack. OH minus is doing a nucleophilic attack on this carb cation from top. So what we get is this. Now when you compare this structure with this structure, Cl has disappeared and OH has appeared in the same location, top, when OH minus is attacking from top. Alright, now when OH minus is attacking from bottom, OH, instead of Cl being there, instead of the group being there, the group is down here. So group is down here, OH. So when this happens, we call it as retention. Why? Because Cl was at the top and OH also has come at the top. Whereas when this happens, we call it as inversion. Why? Because Cl was at the top, but inversion, inverted. OH has come from bottom. So this is how I show the planar structure. Attacking from bottom, nucleophilic attack from top. So getting retention and inversion 50-50%. Now assume that this is plus isomer and this is negative isomer. This is levorotatory, this is dextrorotatory. 50-50% you get. That is what we call as racemic mixture. So what was the product? The product was, we started with Cl, T-butyl chloride, ended up with T-butyl alcohol, T-butanol. And here also it was racemic mixture. Here also we ended up with racemic mixture. Alright. Now these are two steps which are occurring in this reaction. Now which of the two do you think is fast? Now this is very slow because it is bond breaking. Whereas here it is reaction between two charges. So this would be fast. So this becomes, so in this total reaction, it is this which is very slow. So this becomes RDS, that is rate determining step. Alright, then when we draw energy profile, now energy profile, it is in 2 steps, so it would be something like this. Alright, this is, suppose, assume this to be energy, this is reaction coordinate. So we find that breaking requires more energy than making. This is making, this is breaking. So this is what is for step 1 and this is what is for step 2. Now this, we also put it absolutely unstable. So we call this as TS, that is transition state. TS, that is transition state. Alright, so these are transition states, and this one is bond breaking, high energy, and this is bond making, low energy, slow step, fast step, transition state. It is absolutely unstable. As soon as this is formed, it has to form this. Alright, so this is what also we have to keep in mind when we talk in terms of substitution nucleophilic first order. And why do we call it a first order reaction? Because if you check out in rate determining step, what do you find? You find that only this is involved in rate determining step. That is only one of the 2 bimolecular reaction, but out of this bimolecular reaction, only one of the molecule is involved, not both the reactants. So it is SN1 mechanism. Whereas when we go to SN2 mechanism, you would find that both the molecules would be involved in transition state, and that's the reason why it would be substitution. Why substitution? Why? Because Cl has been substituted by OH. So substitution. Why nucleophilic? Now you know, because it has done nucleophilic reaction. So substitution, because Cl substituted by OH, and nucleophilic because nucleophilic attack. Alright, and first order. Why first order? Because in rate determining step, it is only this molecule, only this one, not this, only this one is involved. So alright, so that's all about SN1 mechanism.